So now let's continue to the forced vibration response, and in that let me first discuss the harmonic response, because that was the very first topic which we discussed after free vibration. So the question in this particular example was that using ETABS or SAP 2000, you apply a harmonic loading to your computer model and calculate the response as predicted by a commercial software package, and then compare it with your analytical response calculated maybe using hand calculation or using Excel sheet or anything. So the applied loading had an amplitude of 1000 Newton, and the applied loading have a frequency which was given in the form of the natural frequency of the structure itself. So if the natural frequency of the structure is F, the first case of applied loading is that the applied loading have a frequency F bar equal to 1/4 of the natural frequency of the structure, 0.25 F. Similarly, another loading case for 0.5 F, then 0.9 F, F bar equal to F, which is the exact resonance case, and then more than the F bar is more than the applied natural frequency of the structure, which is 1.1, 2 or 3. In all of those, we assume initial rest conditions, so initial displacement, initial velocity are all 0. So we have already worked out the time period, and that can be converted into the natural frequency. So time period is already calculated. It is for this particular structure it is 0.314. So T is 0.314 second. This can be reciprocated to calculate F, which is 1 over 0.314. It will be in Hertz. So that F can be further used in this second task, which is the response of that single degree of freedom system against a harmonic loading. So for first case, for example, it will be 1/4 of F. So P0 and F bar is already available. So we are given with the harmonic loading, and we want to now apply to our computer model and predict response using ETABS. So let me now go back and apply a harmonic loading to this single degree of freedom system model. Let me unlock it again, and let me quickly go through this process, because this might already be familiar with you, this process. In ETABS, you might know already that we have first load patterns, then we apply loading in those load patterns. Those load patterns are called in load cases. Analysis is performed for load cases, and then load combinations in load cases are called in load combinations. Combinations are used for the purpose of structural design. Analysis is not run for load combinations, it is run for load cases, and then the results are combined using different load factors which you define in load cases, and then the combined results are also presented by the program after the analysis. So this is the overall hierarchy. We start with load pattern, then load cases, and then load combo. So in order to apply a harmonic load, let's say at any point, let's say this node number 1, I want to apply a harmonic load in horizontal direction in the only available degree of freedom. So I first have to define the time variation of applied loading. For static load, the process is simple, that you select that node, go to assign, joint load, and then force. This process is basically for static loading. You apply any point load in any of the 6 available degrees of freedom and put that in some pattern which you should have first made, and then click on apply. So static load is applied already. That process is very simple. But for dynamic load, you first have to define the time variation of that load, and then you can apply some load and associate a time variation to that load. So for that, the process starts with going to define and this functions. This function have two purposes actually. One is to define the response spectrum for the purpose of response spectrum analysis of buildings. It is one of the seismic analysis procedures. And second is time history. Time history can be used for both purposes. It can be used for the earthquake analysis, or it can also be used to define the time variation of any applied loading that can represent any real loading source, for example, an eccentric motor or any other source of vibration. So I can click on this time history, and this will give me a new form where I can define the time variation of my applied loading. It can be time variation of some loading also, as well as the ground acceleration history also, for the purpose of time history analysis in seismic analysis procedures. That we will define when we will be defining the load pattern and load cases. So first let's quickly define a sine function. So here there are already pre-existing functions available. We can use any of them. We can also define a time variation from file, or point by point I can enter that using the user option, or I can use any of the available template. For example, for sinusoidal loading, the template is already available in the form of this sine. So let me select that and add a new function, and then we will be given with this form. Here I have to define a sine function, right? And then later I will assign this sine function to a loading. That loading will become dynamic. That will become time varying loading. So the time period of that function we have to provide. So let's say 1 second is the time period of that loading. And then the number of steps per cycle. The program actually follows the step-by-step direct integration method. It doesn't follow the classical solution method which we discussed in the classroom for harmonic loading. Actually, for any kind of dynamic loading, it follows the step-by-step direct integration scheme. So therefore, it must require the number of steps per cycle to make that sinusoidal loading. If I give too less number of steps, the loading will not be that smooth. For example, let me give just 5 cycles. So you can see that now each cycle, okay, it cannot be less than 8. Okay, let me just make it 8. So you can see that now each cycle of the applied loading or variation is comprising of 8 points only. But if I give 20, it will become very smooth. The number of cycles to be applied, or number of cycles of the time variation of applied loading. So 1 second is the time period of that, and I apply 5 cycles, it will become a 5 second of time history. So you can see here that it is total 5 second time history. Let me make it 10 cycles. So it is now 10 cycles. The form is changed now. Amplitude is 1. Actually, this is the amplitude of this function, right? So we can have two approaches here. Since our amplitude of applied loading in the given problem is 1000 newtons, right? So either we can just give a 1000 Newton amplitude to our variation and just apply a point load of 1 Newton and give this time history to that 1 Newton. It will simply be multiplied by 1 Newton, and that will become a 1000 Newtons time varying applied loading. Or alternatively, what we can do is that we can just keep the amplitude equal to 1 and apply a 1000 Newton force and then give this time history to that 1000 Newton. It will be same thing. So let's just keep that amplitude equal to 1, and the program automatically redraws whenever we make a change here. We have to give some name to this function also. So let me just give sine loading, or maybe let's say let's call it sine function. So this is sine function. Currently it is not a loading, it is just a function or variation which we are currently defining. Later we will associate that with some applied loading, or we'll attach that to some applied loading. If I click on convert to user defined, the whole loading will be converted to a table which I can define. I can modify any entry in that table. So let's not go into that detail and just click OK. So now that sine function now is available in that list of available functions. So let me click OK. So now I have a function which is having a sine variation. It has a certain frequency which is set as 1 second time period or 1 hertz, and it has an amplitude of 1 unity amplitude, and it has a duration of 10 seconds. So whatever is the condition for my real loading case, I will depict that in my sine variation. Let's say that I have a particular vibrating motor installed to my structure, and it has a natural frequency or natural time period of 0.5 second. That motor applies a loading which completes one cycle of loading in 0.5 second. In that case, I should give 0.5 second here, and then number of steps can be remain, it can be 20. The number of cycles will be simply telling us how much duration for which the applied loading should be sustained, for which we want to perform the dynamic analysis. It will be simply the total duration will be simply number of cycles multiplied by the time period which we give. So currently we have 1 second time period of applied loadings variation and 10 number of cycles, so it actually gives us a 10 second of applied loading. But we can change this number also if we want for any other duration. There is a guideline also about that. The loading duration should be sufficient enough to excite all vibration modes of your structure. So if your structure is subjected to sustained loading of harmonic nature, you should perform that analysis for enough number of seconds, so that if your building wants to exhibit the resonance phenomena, it have enough time to develop that resonance response, so that your analysis is technically correct. So if you remember that resonance have certain conditions. First condition was that the natural frequency of applied loading, the frequency of applied loading should match with the natural frequency of your structure. But one of the condition was also that the loading should sustain for a sufficient duration of time. So if you have an eccentric motor installed on your structure and your time period of your structure is 5 seconds, you should go for maybe 50 second or 60 or 80 second of time history, so that the building have enough time to develop the response or build that response if it wants to build. That will be the correct way to perform dynamic analysis. So I assume that now you are clear with how you should be able to provide all that information. So for this particular case, let's say I go for the first case. Let's say my natural frequency is around 1 hertz, and here the F bar turns out to be 0.25 hertz. So here I should give a time period which is corresponding to 0.25 hertz. Here in ETABS, the time period of applied loading should be 1 over 0.25 hertz. Similarly, the number of steps that can remain like this. The number of cycles should be based on how much duration for which you want to perform the analysis, and amplitude can be left as 1. So once that function is defined, now we can apply some loading. Actually, we can apply 1000 kilonewton or 1000 Newton force equal to P naught at this particular node 1 in horizontal direction, and then make a load case in which we associate the time variation to this 1000 Newton. This will make that 1000 Newton dynamic, a dynamic loading. So let's first define a load pattern in which we will first add some 1000 Newton load. So let me just make a pattern. One pattern is already made harmonic, and its type is other, because there is no other type which matches with this, so I just select other. So harmonic loading is already this pattern is already defined. Currently there is no load value in that pattern. We have to define that manually. So we'll simply select this node, go to assign, and then joint load and force, and in the global x direction of our model, this one, we simply apply 1000 Newton or 1 kilonewton. By default my units are in kilonewton, so I'll simply click 1. But that should be added to my harmonic load pattern. So let's add that here, 1000 Newton, which is equal to P naught, and let's apply. So that 1000 Newton or 1 kilonewton is now applied here, but currently it is static loading. We have to convert it into dynamic loading by attaching a time history with it. So that we will do in making a load case. So once we define a harmonic pattern, we apply the static harmonic loading, actually static loading, which we have to make it dynamic. So we will go to define load cases, and in that I will be making a new load case. Let's not use the default one. Let's make a new load case, and let's select the load case type as the time history load case. So time history load case is actually the dynamic analysis load case. So let me just call it as sine load case. And in that I again have to select one of these four options. Linear model, these are actually the analysis procedures within time history analysis method. Linear model will make use of the mode shapes, and it is the modal response history analysis. Then nonlinear model is fast nonlinear analysis. Then we have the linear direct integration and nonlinear direct integration. Since our computer model currently is linear, so only we can have linear model and then linear direct integration. The analysis procedure for both of them is different. How the dynamic response is computed in both of them is different. So in one of the lectures it is covered also that what is the underlying mathematical formulation of linear response history analysis, modal response history analysis. It is based on the concept of mode shapes and uncoupling of the equation of motion. Linear direct integration doesn't make use of mode shape concept. It simply uses the incremental form of governing equation of motion and solve them step by step manner to calculate directly the combined dynamic response. So we can either use linear model or linear direct integration. The inputs required in both of these analysis or solution methods is slightly different. So let me just select linear direct integration in this particular case, and then we have to select if any of the p delta options are required to be included or not. So let's not include that because our theoretical model doesn't include that. So loads applied, I should add the loading which should be applied as part of this load case. So first I should select the load type, which is a pattern, load pattern. The alternating is the acceleration. This option will be used if you want to apply the earthquake analysis or dynamic analysis for seismic loading, which is the linear or non-linear time history analysis. So currently I want to apply a dynamic loading, so therefore I go for load pattern, and the pattern name is harmonic. Now I know that in that pattern that 1000 Newton load is being applied. So that pattern is selected. Then we can associate a function with that pattern. So let's associate that sine function with it. So once we do that, now this 1000 Newton load becomes harmonic load, because now a time history is given to it. So that time history will be multiplied by that 1000 Newton, and now it becomes a sinusoidal loading, gentle push and a gentle pull. So the amplitude of sine function was equal to 1, and the amplitude of harmonic loading, which was applied as a point load, was 1000 Newton. So when these two things will be multiplied, we will be exactly getting the same harmonic loading, having an amplitude of 1000 Newton and having a time variation which is defined by our function, sine function. So if we want to apply an additional scale factor, we can do that, but let's keep it 1. The number of output time steps, they should match with the time step of your function if you want to see the results for each of the load case. So let me quickly go back and let me quickly click OK and go to my function and then same sine function. So you can see here that it is actually 10 seconds of time history. Each cycle have 20 number of steps and there are 10 cycles. So which means that there are total of 200 steps in this whole 10-second time history. And the delta t, which means that how these steps are you can say spaced, it is simply equal to the duration of one cycle divided by the number of steps in that cycle. This will give me the delta t or the time interval. So the duration of one cycle is 1 second and there are total 20 steps in one cycle. So this will give me 1 over 20 will give me 0.05 is my time interval for each step and the total number of steps is 200. So let's take these two numbers and come back here, define and then load cases, and within the same linear direct integration load case I can modify that and put the same two numbers here which I worked out. So the total number of output time steps should be equal to 200 so that I can get the output for each of the time step of applied loading. The total time steps in the applied loading were 200 also. And the output time step size, let's make it equal to the same as the time step of the input function so that we get the output for each of the time step. Then finally we have to select these two things. One is what damping this system should have. This is the information required by the program to construct the damping matrix of our structure. So currently it is a very simple model, but still the input is required. So let me click on modify show, and here I have several options to define the damping. Actually it uses two models. ETABS uses either the viscous proportional damping or also sometimes called as the Rayleigh damping, and it also has the modal damping option. Rayleigh damping is controlled by two coefficients. One is the mass proportional coefficient and other is the stiffness proportional coefficient. I can directly define them and then it will be used to construct the C matrix. Or I can specify some value of damping which I want to give to particular time period, and the program will be able to recalculate those coefficients which will ensure that damping. So let's say I say that for first 1 second time period my damping should be 0.05 and for 0.1 second it should be 0.01, and then program can automatically calculate A0 and A1 coefficients, or sometimes also called as alpha and beta coefficients for viscous proportional damping. And third option is by frequency, that instead of giving a time period and damping I give a frequency and damping. Same thing. Additionally, I can include the modal damping, and in modal damping if I click on modify show modal parameters, again a new form will appear in which I can either use a constant modal damping for each mode, or I can go for interpolated value between frequency or period, and then mass and stiffness proportional damping can also be included, converted into modal damping and then included in the overall damping. So let's simply just use some value. Obviously if in our problem a damping ratio of 5% is given, this one, so a damping of 5% is given, let's say. So let's go with the modal damping option and just select 5% for all the modes, although this structure have only one mode. So let me just go back and click on this damping option again. Let me include modal damping only and directly give a constant modal damping first option and then 0.05 value for each mode, although it have only one mode. So I can click on OK and OK. So now it has a modal damping of 5%. It has only one mode, so this structure have a 5% damping now. So we have ensured that this structure should have the same mass as the given problem. It has the same stiffness, and now we also ensure that it has the same damping which is given in our problem. and we have applied it with a sinusoidal loading having an amplitude equal to 1000 Newton and having a particular frequency equal to 1 second, for example. The last thing in this load case is the time integration method. Since we have used the linear direct integration approach at the top, so we have to select an integration method also. So generally this HHT method is used, but you can also go for Newmark, Wilson theta, or any other method. Actually, Newmark method, one of the many available Newmark methods, is also discussed in our classroom also for single degree of freedom systems and then for multiple degree of freedom systems also. But let's just go with this HHT method, default one. So when I click OK, the load case for the sinusoidal loading is applied already. And now I am able to run the analysis for this dynamic loading. All the results which I obtain after this load case is run, all the results will be time dependent. They will not be static one number for each response. It will be for whole 10 second of time history, right? So if I click OK, now the load case is ready for running the analysis. But before running the analysis, I would also like to cover some of the other types of dynamic loading, and that can easily be defined in the same define functions option. For example, if I want to define a periodic loading, so I'll go to time history and I can go for this user periodic option, or I can also go for any template, for example triangular or sawtooth or ramp or any other. So let's for example go for triangular loading and add new function. So by default you will see that it is already a periodic loading having a triangular shape. We can change its time period, let's say 0.5 second, and then we can go for the number of cycles, let's say 20 number of cycles. So you will see that there will be 20 number of cycles. Amplitude also. So whatever controlling parameters we give, the table will be automatically adjusted and the graph will be automatically modified. Same is the case for any other loading, for example this sawtooth. So I will add new function and it is this sawtooth loading. I can modify its time period, number of cycles, let's say, again I make it 20, let's say, and then I can change its time period and number of cycles to get any duration of applied loading. Similarly, I can go for user periodic. In this, I have to just define one cycle of the periodic loading and then give the number of cycles. It will replicate those cycles for those number of cycles and make the whole loading as periodic. For example, I say that this is a loading, let's define first cycle, time equal to 0, value equal to 0, let's add that point. Then time equal to 1 second, or let's say 0.1 second, and loading value is let's say 10. So let's add that. So if this is only one cycle, 0 and then 10, then again 0 and 10. So the program will repeat that same pattern for as many number of cycles as you want. For example, let me change it to 10 cycles. So when I click somewhere else, it will automatically modify for 10 cycles, 10 number of cycles. So you can see the duration will be accordingly modified. You can also convert it into user defined. I can also add some other one. For example, let me add it 0.2 and make it let's say 5 second and add. So now the program consider these 3 points as one cycle and keep on repeating these 3 points again and again for 10 number of cycles, right? So using this option, I can make any shape I want for the applied loading. I can use this option to define any type of dynamic loading. Let's take the case of impulse loading, a sudden increase in loading, then sudden reduction, and then constant. We can also use the same option for defining an impulse loading. Although the impulse loading doesn't have a default template, but let's use, for example, user option here. Here I will point by point define my loading. So let me click on add new function and let's say I say 0 time and 0 value, and then for very small 0.001 time I have a value of, let's say, 1000 Newton or some high value. Click on add, and then right at the next step 0.002 the value again reduced to 0, right? So let me add that. So it just increase, and then right at the next step it again becomes 0. Then for all the next steps, for example up till 10 seconds, the value will remain 0. So let me directly define a next number, let's say 1 second, and value is 0. Let's say not 1 second, 1 will be too high, maybe 0.01 and modify. So you can see that now it become and kind of an impulse loading, maybe 0.02 also, and again have the value equal to 0, 0.03 again value equal to 0, and maybe 0.05 also. So that's how you can make any impulse loading also. You just define your amplitude and make apply a unit load at any location where you want to apply impulse load, and assign this time history to that unit load, and that unit load will be converted into an impulse loading with this variation. So any kind of or any shape of impulse can also be made. For example, half cycle pulse, either I can use the user defined option for that, half sine pulse. So either I can use the user definition here. I can manually enter one half cycle pulse, and then all the other points will be 0. Or I can also use some sine function option. For example, use sine, add new function, and just use one number of cycle. So it is one cycle, and then maybe convert it into user defined. So this has 1 second of period. So after 0.5 second, the value should be flat horizontal for all the next time intervals. So for that I can start like this, can give any time period which I want for that half cycle, and then I convert it into user defined. When I click that, it gives me the same function in the form of a table, which I can also modify and add new points also. So after 0.5 second, maybe this is okay, but beyond that I can make all the other points equal to 0. So for 5.5 I can just make it at equal to 0 and modify. Similarly for all the next points also, for 0.6 I can make it 0 and modify, and keep on doing it until I get my desired shape. Let's say it is also 0, then next is also 0. Same is the case for this one, 0. And let's do one more thing, is let's just delete all the next points and add our own points. So let me just delete this one, then this one also, this one also, this one. So now we have 1 second of time history, which 0.5 second have a half sine pulse, and all other values are 0. So let me just add another point, like 2 second value is still 0, and click on add. Then 3 second value is still 0, click on add. Or maybe 5 second value is still 0 and click on add. So that's how I can make an impulse loading which have a half sine pulse shape, or any other shape. Rectangular pulse also you can make, or triangular pulse, or any other shape. So that's how, using these features of functions, these functions option, define functions, you can make any variation and associate that variation with any applied loading. That loading will become dynamic with that variation. So if I want to apply, for example, some impulse loading at this particular location, I should apply a load here and associate that function 5, for example, which was the pulse function, associate that with that loading while making a load case. So that's how we can cover harmonic loading, we can cover periodic impulse, We can even cover general dynamic loading or any other dynamic loading as long as we can define it as a function in this ETABS environment. So once we develop that model and we apply the loading also, dynamic loading, and the procedure will be same for even complex structures also. I am only using a single degree of freedom system for this demonstration, but even if it was some complex structure and there is a point load which is dynamic in nature, the process is exactly same. That you have to define a time variation first, time history, and then associate that with some applied loading that will make that applied loading dynamic in nature. So for this particular harmonic case, let me go to my load cases, and I think I already run the harmonic case, and the results are already available. So let me quickly review these two load cases also. Harmonic, which was previously there already, which I made that already. So it makes use of a load pattern which is called harmonic and a load function which is also harmonic. So let me review these two inputs. I go to function and then I go to time history, and there is a harmonic pattern already. So let me modify that. So it is already a harmonic loading with 50 steps per cycle, having a period equal to this one. I think it is exactly matching with what is required in that particular question which I was following, right? But whatever the value of f bar is, you convert that, you reciprocate that and convert it into time period t bar and put that number here in the period of applied loading. And then number of cycles is 10, which makes it a total time history of 9 seconds, and amplitude is set equal to 1. Then I also defined another load pattern called harmonic truncated, and in that I actually truncate the harmonic loading at 9th second and continue the points up till 15th second. So the analysis will be run for 15 seconds, but the applied loading I know already that it becomes 0 at 9 seconds, right? So I'll see the response, and we will see that after 9 seconds, the building will follow its own natural time period, right? Because it will be free vibration response. So let me directly open a model which is run for this harmonic loading. Actually for both loadings, complete harmonic loading for 9 seconds and a loading for 15 seconds, in which after 9 seconds the value of loading becomes 0. So let me open that model which is run already to show you some of the sample results and how they are matching with the analytical solution. So this model is logged already, it is run already for the dynamic loading. So let me directly go to display and let me use the plot functions option to plot the displacement of any of these nodes, let's say 1, 5 or 2, right? So let me go to display and plot functions after running the analysis, and here I can select the load case as harmonic first, horizontal function should be time, and vertical function should be the displacement, and I have to select the displacement of a particular node. So I can click on this symbol here, f of x, to select which node should be having a displacement on the vertical axis. So currently you can see here that I have selected the story 1 and joint label 5, and the horizontal displacement ux is being plotted as a function of time on this graph. So if I go to my model and see what is the joint label 5, it will be exactly, I think, the middle of the beam. So let me go to that view. So this is joint 5. So which means that I am plotting the displacement of this beam, which is a rigid beam actually, after the analysis, and that analysis is harmonic. So you can see here that for all 9 seconds, the structure is vibrating a harmonic manner which is confirmed by our numerical analytical calculation. One observation you can have is that for 1 or 2 cycles, the amplitude is more than the constant amplitude which is being depicted here. And you can guess that the first 1 or 2 cycles, they are actually the homogeneous part of the solution, and then after that is the steady state response. So actually when we compare the peak amplitude, it should actually be the steady state response only, because homogeneous part of the solution we although can calculate analytically, but let's just simply compare the steady state response only. So I will go back to the same Excel sheet and show you the results in the form which I plotted here. So you can see here that this is the analytical steady state response against the harmonic loading which was given, and the peak value is somewhere around 0.69, and it is for all 9 seconds of time history. So although you can run it or you can plot the analytical solution for any number of seconds, but in ETABS we run it only for 9 seconds. So you can see here that the peak response is very close to the analytical response which I am getting. For example, here the value is shown here. The maximum value is obviously it is 0.9, but that corresponds to the homogeneous part of the solution, first few cycles. But once the solution reaches the steady state, I can click on this point or I can keep the cursor here, and at the bottom you will see that the cursor is snapped to a value of 0.707. Somewhere here you will see that my maximum value or my cursor location will come, and it is 0.7. The analytical solution was also 0.7, exactly 0.7. So which means that the harmonic response in ETABS is exactly matching with the response which which is calculated using the closed form classical solution. Now the program is using the HHT method. It is one of the step-by-step direct integration method. The classical solution is using a closed form equation to get the same number or same peak displacement. Now let's plot the displacement of the same point, displacement of beam, against the truncated harmonic applied loading. So if you remember that it was a 15-second time history, but for first 9 seconds the harmonic loading was there, and after that it suddenly becomes 0. So you can see here that program actually calculate the response for all 15 seconds for displacement response, and again the peak amplitude is matching with what we calculate analytically. But once the loading becomes 0, the structure starts following its own natural frequency. So all those cycles which are here after 9 seconds, they are the free vibration response of our structure with 5% damping which we give. So you can see here that the effect of damping was negligible in the forced vibration case, but in the free vibration case the damping starts reducing the amplitude depending upon the value of damping ratio which we give. So in just few cycles the amplitude reduced to a negligible number. So if you closely look at this area, free vibration response, you will see that on average one cycle is being completed in 0.314 seconds, which is equal to the natural time period of your structure, which again confirms that natural time period is the time period which the structure would like to vibrate in if it is allowed to vibrate freely without the influence of any applied loading. So you can count that from the time required to complete one cycle will be equal to the number which is calculated as the natural time period, 0.314 seconds. So there can be several of the observations you can have from these plots. You can save these plots in the form of formatted data, time history and displacement, and then copy that to Excel, plot it yourself, or any other processing you want to do. The options are available. So all the other responses also, for example, forces in columns, shear force, bending moment, all other responses will be calculated for whole of the duration. Let's say if the time history was 15 seconds, the value will be calculated for all of 15-second duration. And then you can make a practical design decision making on after looking at the complete time history of response, whether you have to pick the peak number or you have to pick the root mean square of few peaks, etc., etc. So, although I can explain more about some of the analysis output capabilities, but I think you might already be familiar with basic static analysis in ETABS, so therefore the same options are used with one difference, that now all the you can say output or response quantities will not be one number just in case of static analysis. They will be actually the time functions. So reactions will be time functions, displacements will be time functions, shear force bending moments will be time functions. Every response will be now the function of time. So several of the other analysis or output capabilities you can explore, but they are common options for static and dynamic analysis with that one difference.